Good morning, everybody. Welcome here to vBrownBag on using machine learning for workload analysis and placement in the cloud. So, my name is Kenneth Moore. I am a data and functional engineer within Dell EMC. I work in the Converged Solutions and Platforms division. So, my background is in machine learning. It's in machine learning and workload analysis, machine learning and configuration architecture. What I'm going to show you today can be applied to both hardware and software, so it can be applied to VM deployment or converged infrastructure deployment. And a lot of what I'm doing is working with crowdsourced data. How can I use crowdsourced data in the work that I'm doing? And I have a couple of patents on this topic. So what I'm going to show you today, right? Simple question. Can we use crowdsourced data to design more efficient systems? Can we optimize our designs using crowdsourced data? Some people are going to say, well, VMware has a whole suite of tools here, vMotion, DRS, resource over subscription, and that provides optimization already in your design. So why would I want to work in this area? Well, it's simple. That work is in your production environment. Your architecture is already in place. You can't change that architecture. What I want to take how you use that information, bring it back to design phase, and then design more better and more efficient systems, right? So the data we have there is going to be in our design environment. A simple story, right? And this gives us a good example of what I'm trying to do here. The Goldilocks problem or Goldilocks principle, right? Goldilocks comes in, she looks for some porridge. And that's all she's asked for is porridge. We've given her 3 bowls. And out of those 3 bowls, one is too hot, one is too cold, and one is just right. So, why did it take us 3 times to get this right? So, how can we go forward and improve upon that? We can learn from this. We know Goldilocks and Baby Bear are similar. From this experiment we've just done, we know they have similar properties. So now, anytime somebody like Goldilocks or Baby Bear comes along, we know exactly what to give them. But we also know what Mommy Bear and Daddy Bear like, right? So we can introduce a new variable. We can introduce Uncle Bear. We know Uncle Bear is very similar to Daddy Bear. So it makes it very easy to give Uncle Bear his bowl of porridge. So it's a simple story, but what does it do for us? It tells us how we can use crowdsourced data to make our designs more efficient and get it right first time up. So, where's our starting point? Our starting point is our shopping list, right? And when we take that shopping list, we want to put that shopping list through a modeling system. And out of the other side of the modeling system, we want to get a solution that provides the benefits that the shopping list has asked for. We're going to develop a machine learning artificial environment around that whole problem. We started with a data lake, right? Now, a data lake, what is it? It's a place for storing data. But like any lake, it has an input and output, right? It flows in with relevant information, and then old information flows out. How long you keep that data in that data lake is up to you, but it needs to be relevant to your current machine learning needs. We want to populate that data. Where do we get that data lake? Where do we get that data from? We're going to go to the field. We're going to go to systems in production, and we're going to pull the telemetry data. We're going to pull the health data. We're going to pull the system logs, and anything else that's relevant to us understanding how that infrastructure is operating. What's relevant here as well is we need to know what the configuration of that system is, but our telemetry data will give us that. We pipe that back to our data lake, and we populate the data into our data lake. So what we're populating in here is quality of service metrics. That tells us how our system is operating. It tells us, by the way, which systems are operating well, which systems are operating not so well. We're going to populate that with our crowdsourced data. So this is many sources from many different locations, many different configurations, but it's all relevant to building up a picture and a profile. We want to pull out industry verticals out of that data. So we want to know, are you working in pharmaceutical, medical devices, oil and gas, it doesn't matter, right? But we want to build a trend, we want to build a pattern out of the data that we're putting in here so we can use that data going forward. We want to know where you're located, geotagging, right? Because I've seen in my experiments that what's relevant to somebody in the US or Europe or Asia, their perception of whether they go cost versus performance or performance versus cost in their decision making varies from geography to geography. So let's use everything we can to help you gear towards the right direction. We're going to take all that data in the data lake, and it's relevant for storage, but we need to do something with it. So we're going to pass it through a machine learning engine. We're going to learn about it, but we're going to learn the relevance of the problem we're trying to solve. Once we've done that, we can pass it into an artificial intelligence engine. And that artificial intelligence engine is our modeling environment. Now our environment is set up. We can take our shopping list, pass it through the artificial intelligence engine, and get a recommendation out the other side. So how are we going to do this, right? There's two key things here that I need to talk about. I'm going to talk about the machine learning engine. I'm going to talk about the artificial intelligence engine. So machine learning engine, right? What's in it? It's an analytical engine. It's going to take our data. It's going to take our telemetry data. It's going to take our health data. And it's going to cluster that data, right? And it's going to create patterns of usage based on our industry verticals, our geography, us as a customer base, and anything else we're doing. Are we using Excel? Are we using Oracle? Are we using SAP? It's going to cluster all this data. We're going to put some trend analysis around it. We want to find outliers out of that data. Because, for example, if your health data is telling you that you've got CRC problems in your storage, is that because you just got a bad disk, or is it because you've got a bad design? Right? So we want outliers, and we need to look at these outliers and decide whether we're going to stay in them or go out of them. We're going to do some normal distribution, which tells us what are our normalities in that particular pattern. Now, this is where we're getting our benefit from the crowdsource. We're going to see what other people are doing in our industry that's relevant to what we're doing, which will help us gear our designs. And then we apply our statistical analysis maths. So we've got means, weighted means, z-scores, standard deviation, etc., etc. That comes together as our data models, right? These data models are representations of the data we have in our data lake. How do they look, right? How do we visualize them? They're lookup tables, they're mathematical formulas, they're decision trees, right? Effectively, our data models that we've gained from our machine learning engine are compressed formats of our original data set. They're compressed formats because now we can deploy them in small packages out to our configuration and recommendation system, right? And also it means that when we are going through our artificial intelligence system, we're not trawling through mountains of data that's in the lake, we're just going through these quick lookup systems to match our models. Our artificial intelligence engine. So, we're going to take our shopping list, we need a specification. But our specification isn't complete here, right? So this is the first part of our artificial intelligence engine. How can we use that data we just hid in our workload, in our modeling system, to fill in the gaps, right? Those gaps that we just filled in came from similarities to other use cases. Second stage is our recommendation engine, right? So because we know the full specification now, because we filled in the gaps, we can recommend more than one product. And actually in the artificial intelligence world, we want that. We want a space, or we call it a state space, of many solutions that does the job. But now that complicates things, because how do we decide what do we want? Well, we use search optimization, right? This is another part of our artificial intelligence engine, right? So I'm going to take two parameters here. I'm going to take performance and cost. And in my performance and cost, I want to compare them, and I want to see, am I getting value out of my design set? So, well, the first thing I want is I want to normalize my data, because I want whatever I present up on this chart to be relevant to the current design needs. I want it to be something that we can visualize very quickly, very easily. So I'm going to look at it as a percentage of our needs. Are we getting 100% of the performance we asked for? Are we getting 100% of the cost we asked for, right? Or if we want to optimize and improve that, are we getting more than 100% cost? Are we getting less than our budget? Of course, if we get it for 75% of our budget, everyone's happy, right? And if we get 125% performance for 75% of our budget, everyone's even more happier, right? So we also need to take into consideration here, because I did a min-max scenario here, it's going to be hard to plot that on the chart and visualize. I want to push things away from the origin, you see. So I'm going to do a negative inverse power on my cost, and that allows me to push the cost out away from the zero of my chart. Now, I bring up some solutions. Here there's about, 10 solutions. All 10 solutions will do the job for the specification that was asked for originally. Great. Which one do I pick? Which is the best one here to offer to the customer? Or if I am a customer deploying virtual machines, which one is it, the one that I'm going to go with? Well, I look at my ideal scenario. I want to balance performance versus cost. And the best performance versus cost is going to be along the northeast quadrant trajectory, right? So now straight away we start seeing patterns. We've got a couple of solutions here which are lying along that path. So, maybe we go for the second one here because it's on the path and it's quite high up. But let's give ourselves a chance here. Let's just allow a little bit of assumption that if we give and take on certain areas, can we do something slightly better, right? So we're going to give ourselves a buffer zone of good fit. And in that buffer zone a good fit, we weed out a couple of them. So this is the first step of our search optimization. In this, what we're doing is we're doing heuristic traversion, right? So we're taking our heuristic here being performance versus cost, and we're navigating through that to find the best one. And this is where artificial intelligence comes into its own, right? It's not the first answer is the right one. It's using that heuristic measurement to navigate through other solutions and find a better one, right? Second iteration of it, we're going to look at deviation from the northeast trajectory. So we're down to 3 solutions that could potentially work here, right? And we're giving ourselves, in this case, I was giving myself maybe a 5% buffer zone, right? And the last piece then I go back and find what's the nearest one. Here's my best fit. This is the one that I'm going to use, right? There's a little bit of give and take, but because I went with the XY axis and I went with unity normalization, the further away from 0, the better it is for me on both axes, right? This process that I just introduced here, is a hill climbing process. And anybody in the artificial intelligence world will know that, hill climbing, you start climbing a hill. How do we find the peak of that hill? And that's what we're doing here. We're navigating up a hill. And we're looking at different values till we figure out what is the highest we can achieve. So there's a problem here, right? I just showed you performance versus cost. That's only a slice of the whole problem. In reality, designing systems has multiple attributes to consider. And that specification that we came up with a while ago that we filled in the gaps could be hundreds of attributes that we want to consider. So we actually have a Euclidean space here, right? And a Euclidean space is taking all the attributes, comparing them all to each other and making it far more complicated. But because it is a Euclidean space, we can use Euclidean maths to pull it all back in and give us a heuristic. So what we showed there is just a subset of the overall problem. So what are the key takeaways from this session, right? How can I simplify what I just spoke about? We're going to take data from known systems in the field that work, from many different sources. We're going to analyze that data through multiple means, and we're going to create data sets. And those data sets are models that we can use for designing and testing. Once we've designed and tested them, we can deploy, we can adjust, we can refine. And you see, here's the thing. Just because the first iteration gave me a recommended solution and I deployed that out to a particular area, right? It doesn't necessarily mean that we finish there. We now analyze and we keep track of that system and we see how does it perform. We assumed it was going to perform well because that's what our analytics told us. But now we go back and readjust that again and see, did we get what we expected or do we need to refine our models? And we go through this continuous cycle of collect, analyze, model, deploy, collect, analyze, model, deploy. And we keep doing this, right? At a very high level, this has been done through VMware and VCE for years and Dell EMC, right? When VMware came into existence and realized that the CPU could be oversubscribed, they started getting efficiencies, right? And then they deployed vSphere and vCloud Director and all these tool suites, right? But then we come back and look at, well, how can we look at that from a hardware point of view? And then we had the vBlock and the VxRack and the hyperconverged systems coming out, right? So that's a really looking at your data and seeing how can you make something that's already efficient even more efficient. And we can keep doing that over time and time again till you get more and more efficient. And what does that give you? It gives you smaller footprints. It gives you more efficient costing. It gives you a better way of managing your infrastructure needs. It gives you a way of being able to predict what you need in the future and get there ahead of time. So thank you. I'll take some questions offline so we can give the next person a chance to come up.